Hi everyone, we're looking at projectiles in the flat again. We've moved on to chapter 3, section B, page 43. This is question 1. A particle projected with the speed 7√5 meters per second at an angle alpha. Tan alpha is 1/2 from a point on the horizontal plane. Find its initial velocity in terms of I and j and its horizontal range. So here's what we're looking at. You're firing something with the speed 7√5 at an angle such that the tan of the angle is 1/2. Now remember, tan is opposite over adjacent. Okay, our word for remembering all of this is sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent, SOHCAHTOA. So tan is the opposite side here over the adjacent side here. Now, the first part asks you to find the I and j components of that velocity. So what that's called resolving the vector. So this vector of 7√5 at an angle tan inverse 1/2, you want to resolve it into its horizontal and vertical components, or its I and j components as they're also called. So to go about doing that, there's a couple of ways you can do it. The way I'd like you to do it for the moment is using something called a model triangle. And a model triangle does this. It says, I have a triangle which is sides in the ratio 1:2, okay, and you know the speed or the magnitude of the hypotenuse, 7√5. Okay, so that's our angle alpha there with a tan inverse 1/2. Now, if you take this triangle and you do Pythagoras to find the hypotenuse, you'll get 2 squared plus 1 squared and take the square root of. Okay, well that's √5. Now our model triangle here and the triangle we're working up here, because they have the same angle, they both have a 90-degree angle, these are similar triangles, which means you can scale them up. Okay, and you can see here, if that's √5, well that's 7 times bigger, this hypotenuse, which means this side is also 7 times bigger than the opposite side here. It's 7. And you can probably guess that the adjacent side is 14. Okay, so our velocity at the start of this problem as a vector is 14I plus 7j. Okay, and if you looked at the magnitude of that velocity, which you might be asked to do in another question, so I'm just going to show you what that means now. The magnitude of that velocity is written like this. It means how big is it? And that means apply Pythagoras, 14 squared plus 7 squared. And what you'll find is the answer that comes out there, put it into your calculator, is 7√5. Okay, so you need to be able to work forwards and backwards to go from knowing the I and j components to working out the magnitude, and from knowing the magnitude and the angle, work backwards to find the I and j components. Once you have that done, solving this problem is very similar to what we saw in the last set of exercises. Okay, we can say, well, we know in the I direction our initial velocity is 14. In the j direction our initial velocity is 7. We know that the acceleration, as it always is, in the j direction is minus 9.8, and in the I direction it's 0, as long as we're on the flat. And the time for both particles, for both sets of equations is the same, because it's one particle, so the time it's been traveling across and the time it's been traveling perpendicular to the ground are the same. Okay, so here's what we're looking for. This distance along here, which is called the range. We had a condition for it in the last video. See if you remember it there. Maybe pause the video, see if you can write it down, because this is something you should know off by heart. The range condition is that you want to know what is the displacement in the I direction when the displacement in the j direction equals 0. Okay, you've gone up, you've come back down, your total displacement in the j direction is 0. So you come up here, you say, well, the displacement in the j direction is ut plus the half, okay, of a t squared. I've said plus here, but I put in a minus because acceleration is negative. Okay, so I need that to equal 0. 7t minus 4.9 t squared needs to equal 0. Okay, well, solving that, I can spot a common factor of 7 here. So I'm going to divide through t minus 0.7 t squared equals 0. And then taking t as a factor, 1 minus 0.7 t equals 0. Either t equals 0 or 1 minus 0.7 t equals 0. So 1 is 0.7 t, and t is 1 over 0.7, sorry, running out of space here, or 10 sevenths of a second. Okay, multiplying top and bottom there by 10. I didn't talk about it actually in the last video, but this t equals 0 solution, that reflects the fact that at the start of the problem, your displacement is 0, and then at the end of the problem, after 10 over 7 seconds, your displacement is 0. So what's our range? Which is what they've asked for. Well, that's displacement in the I direction, which is ut plus a half of 0 times t squared, which is just 0. So it's 14 times t. So a range here is displacement in the I direction at t equals 10 over 7, which is the time at which we land. So that is going to be 14 times the time, 10 over 7. Okay, common 7 there, top and bottom leaves us with 2 times 10 is 20 meters is our range. Okay, I'm going to ask you to have a look now at question 2. Very similar type of question, except this time you're being asked to find the magnitude of its velocity. So find the velocity in terms of I and j, and then find its magnitude, just like I showed there, the 2 lines either side of velocity that I did in question 1. It's in the opposite direction, I suppose. When it is 10 meters off the ground, so your condition there is displacement in the j direction is 10. What time is that? Plug that back into the question and you'll find its velocity. Right, give it a go. If you're stuck, we'll have a look at it tomorrow. I'm going to leave it there. Okay, thank you.